Thanks, everyone. So I'm here today to talk about crowd simulation and how that fits into the process of design and really how we can put people in design. That's what our buildings are for. That's what our public spaces are for. So let's make sure that we're thinking about that right from the outset. So a number of years ago, I got involved with a project in South Manhattan, the Fulton Center, which some of you may know. It is the connection of 6 different subway lines and a new station right in the midst of the downtown of New York City. And this was a particularly challenging project in terms of the number of people and the new connections that were being created between all these different stations. And we realized Arup, who were the prime design contractor on this, we didn't really know how to answer the question about whether the new design was going to work or not. And so what we started doing, and what I started doing, was looking at developing some algorithms which would actually test how people would elect to move through a complex three-dimensional space in the Fulton Center. So it started in transit, started in rail, but we've in the meantime, continue to evolve the algorithms and the tools to the point where we're using crowd simulation now to do things in airports and stadiums and all kinds of places where you generally find lots of people, lots of complex space, and more particularly, you have some very specific performance criteria that you're interested in. So you may be interested in life safety, or you may be interested in, there we go. You may be interested in the journey times or the comfort of people as they're moving through the space. In all cases, what you're trying to do is make sure that the buildings or the spaces you're designing are as effective as they can be for the people who are going to occupy them. So I love this picture because it is a project that Arup was involved in, although I admit we didn't do any crowd simulation for it. But there's this beautiful, pristine architectural image on the left of the ROM. And then there's the reality of a very busy day with people queuing out the door to get into the building. And that certainly doesn't happen every day. I go there with my kids and it's usually just fine. But it does happen. And what we're really trying to do with crowd simulation is to make sure that these kinds of things don't happen, that the buildings are going to be as functional for people as they can be on the busy days as well as the not so busy days. So I want to talk a little bit about a few things when it comes to crowd simulation. Crowd simulation is actually not that new. It's been around for a while, and there's quite a lot of science and research around it. And then there's the fact that the way people are designing now with BIM and 3D means that there is a really great pipeline of information and data that can be brought into crowd simulation systems. And then a little bit about how we do it. I'm going to give a quick live demo, and I'll be happy to take some questions. So why simulate? The first thing is that you really don't want to have this kind of a condition, which happened a few years ago in a major South American city. And in fairness to that South American city, there was a very significant breakdown of the bus network and a few other things which contributed to this. But you really don't want an environment like this to ever occur. It's not safe, it's not comfortable, and it's not effective. I mean, this is not something which is good for the city when this happens. What you want is something more like this, which is Grand Central Station. It's beautiful, it's airy, it's got lots of people moving through it, and it is effective as a retail environment, as a transit environment, and actually is quite a pleasant place to be. I've had the opportunity to look at a few different things in crowd simulation over the years, and one of the case studies that we did a few years back was looking at the Colosseum in Rome versus the Beijing National Stadium. So 2,000 years difference between these two buildings. The Beijing National Stadium is bigger, in fairness. There are a lot more people in there than there were in the Roman Colosseum, but they still both took about 15 minutes to evacuate, according to our crowd simulations, which I thought was quite interesting. The Romans, through evolution and good thinking, had managed to come up with an incredible system for moving people in and out of stadiums, which we in fact still use today. So we've been worried about crowds for a long time, and the Romans got it right. So why do we care about doing simulation? And for me, the answer to that is that what we're really trying to do here is manage complexity. Yeah, the Colosseum was a big place, and Rome was a pretty big place back in the day, but it's nothing compared to South Manhattan or Union Station here in Toronto. The numbers of people that we're dealing with and the sort of urban fabric that these facilities fit in is so dense and so complicated and so easily disrupted that it is incredibly important that we consider all the possibilities of how the new buildings or the construction we're about to undertake are going to affect the way people move through these environments. So this is another one that we got involved with not long after the Fulton Center.
We can't really hear you.
Oh, I'm sorry. I feel like every time I get close to it, it kind of shrieks at me. All right, is that better? Okay. Sorry, folks. So at Union Station, which probably many of you know, maybe intimately, there's quite a lot of construction going on. And we used this tool to understand what the final design was going to be like, how it was going to work with the city when all was said and done, but also how it was going to work and perform during the construction phasing. I have to say that it wasn't always a win because sometimes the planned construction phasing didn't quite meet up with the plans. But in general, the tool is an incredibly effective way of getting through discussions about how the various projects that are running at Union Station were going to coincide and work together. It's been used in aviation. This is Dubai Airport, all three passenger concourses. And it comes from a long tradition of thinking about, well, I say long in technology terms. It's been around for about 25 years or so, crowd simulation. And it started with very simple block simulation, adjacencies of spaces, as you see on the left, to grid-based systems that you see in the middle left, and then 2D vector-based systems, which actually started to have more dynamic interactions between the people in the simulations. And finally, it's gotten to the point now where we have 3D simulations where there is incredibly sophisticated interaction between the simulated people, each other, and the environments that they're moving through. So, this is basically the same thing with the particular characteristics about it. But the important thing to note here is that there is a fairly rich history of simulation and the advancement in simulation, and it's underpinned by a number of, quite a significant amount of academic work that goes on in universities. And this is kind of where it started. Back in 1971, there was a gentleman named John Fruin who did his PhD on the characteristics of people moving through spaces. He was particularly interested in the area around the World Trade Center and the Port Authority bus terminal, but he also did some of his survey work here in Toronto and some in Montreal as well. And he established what we refer to as levels of service, the sort of characteristics by which, that's not good, by which we judge the comfort of space. So we have 6 different levels of service, from A, which is people moving unencumbered, pretty much at the speed that they want, and, oh my goodness. There we go. All the way to level of service F, which is basically gridlock, people moving people shoulder to shoulder and not being able to move at the speeds that they want to move. And this is what it looks like when you sort of consider people from an overhead view. You've got on the left level of service A, people moving however they want, all the way to people jammed up and not being able to do what they want, sort of queued up like they might be at escalators in a busy transit station. There are also a number of guidelines about how pedestrians need to be planned for in certain things, whether it's stations, whether it's fire and evacuation, or things like stadium grounds. And throughout the world, the London Underground Standard, the NFPA Fire Standard, and the Green Guide for sports grounds tend to be the guides that are used to govern pedestrian performance and requirements. It's also worth pointing out that there is a growing body of sort of validation and verification standards that simulators are expected to meet and be able to conform to. National Institute of Standards in the US publishes one, as does the International Maritime Organization, and they govern things like cruise ships and oil platforms and that sort of thing. So, talking a little bit about how simulation works, it starts with the concept of an agent, a simulated person which has the characteristics of a person. They move at a certain rate, they have a certain size, they prefer to do things in a certain way. Some people will always take the escalator regardless of the size of the queue. Other people are happy to bound up the stairs. And just like people, the agents dynamically assess their environment. So as they encounter congestion, they will consider alternate choices of routes. And they will also try not to run into each other and the environment around them. There's a mathematical formula called social forces, which basically describes the way that people reflexively respond to their environment. So the people around them exert a sort of repelling force, as do obstacles, but they're also trying to achieve local goals, like getting to a doorway or a stairway, and that draws them in a particular direction. And all these different forces get summed up and govern the next step that the agents will take. When it comes to the way that the agents make decisions, effectively what they're doing is making cost optimizations about how they're going to get from where they are to wherever they're going. So what is the horizontal cost of a route that they might take, the vertical cost, including the difference between stairs and escalators, what queuing is there, and to what extent, as they approach, say, a doorway, are there people coming against them, traveling in the opposite direction. And so I want to talk a little bit about the BIM side of things too, because the opportunity with BIM is to be able to, and this will become clear in the demonstration, but the opportunity here is to not just have 3D geometry, but to have objects, so that you actually have floors and you have stairs, and the simulation is able to understand that stuff from the outset. And we've been particularly interested in the industry foundation classes as a way of having a sort of vendor non-specific way of getting information from BIM packages and other design packages into simulation tools. And IFCs are great because they do offer that opportunity, and there seems to be a growing support for it within the industry generally. When the geometry comes in, the simulation software looks at all the objects in the scene, the floors, the doorways, the stairs, escalators, so forth, and algorithms go through the geometry set and work out what the adjacencies are. So this stair connects these two floors and maps out routes throughout the network that the agents will then be able to navigate by. It's also important to establish how many people, whether it's based on train schedules and the occupancy rates of the vehicles from surveys, whether it's going to be based on fire code, and all the different assumptions and the scenarios that you need to take into account when doing your design. There's also complex operational stuff. Do you have things like ticketing, security, check-ins? All of these things can be modeled in these systems. And then finally, there is the running of the simulation and storing data. These simulations can produce quite large amounts of information, but the intent is that once you've got this set of data from the simulation, what you can do is then go in and analyze what the results are, what the performance of that building is going to be in terms of density, journey times, that sort of thing. So, one of the great things about having a simulation, and especially a 3D simulation, is you can do a visual validation of it. You can just look at it and determine whether or not it seems to be making sense or not. Are people going where you expect them to go? Are they being held up in queues? And then there's quantitative analysis, looking at things like overall density, the amount of population that you have in any space over time, and the sort of quality and comfort that people are experiencing as they move through the different areas. And then there is the sort of final stage of doing things, which is communicating the results to people. And there are a number of different ways of doing that. You can do it quantitatively with graphs, and you can also do it through visualization. So it is possible to export crowd simulations to a more advanced visualization tools such as 3D Studio and Maya. So I'm going to show you how this works, because I think that it's actually easier to understand doing it that way than it is to have it explained. So it starts with just an empty space, and just to sort of demonstrate very quickly how the system works, what you can do is just quickly create objects such as floors. So we'll just very quickly create a floor. And now we've got 2 floors. And what we'll do is we'll put a link object in between them, which might represent a doorway, or if you were outside, maybe it would be something like a crosswalk connecting two sidewalks. And so you'll see as I move this around that the object, the link object, is smart enough to know whether it's connected to an appropriate floor object or not. So when the lines turn green, you know that you've got a good connection between things. The other thing which is really important is having the ability to, or an object which represents where agents are going to start and end their journeys. So to do that, we create portal objects. So we'll have a start location and an end location. And now what we need to do is specify for the software where agents are going to start and where they're going to finish. And so to do that, we look at activities and say, right, we're going to create a journey going from the right-hand side to the left-hand side of this. So add that portal, And now what we're seeing here is, well, we're at the beginning of the simulation, we're going to create 100 agents, and they're going to appear over a period of 1 minute. In fact, maybe we'll create a few more. And so that's enough. We've now got enough information for the simulation to run and provide us some, what is admittedly a very simple set of results about this very simple space. All right, so the simulation is run through, and now what we have are agents moving from the right to the left. I'll speed them up a little bit. And so now we can see that they progress, and it's obvious right from the get-go that they don't all fit through that doorway that we've represented in this model. So let's fix that. And we can do that a couple of ways. We can make the link bigger, or we can make a couple of them. So let's make a couple of them. So now we've got 2. If we rerun the simulation, what we'll see now is that because the topology of the scene has changed, the software has taken a look at that change and now made the adjustment so that there are now 2 routes available to the agents. And as congestion builds at one, they'll sort of shift back and forth trying to optimize the space, or their use of the space, such that they get through here as efficiently as possible. So at a really basic level, that's how the simulation software works. This is clearly a trivial example and not that useful. So if we look at something which is a bit more interesting, the one that I'm opening now is an underground light rail station. And in this case, what we've got are what we have is an environment where people are going to be coming from the train cars and going back and forth between the neighborhood and the buses. And let me just see here. I seem to have lost my results set. Brilliant. Okay. Just quickly run a bit more of this. But this is an instance where it is actually starting to become important that you understand how things are going to be working. So are you going to get people crowded at the turnstiles? Are you going to get people effectively getting up and down to the street level and choosing the different exits in and out of the station? Stop that. And so now we can see that we've got people coming on and off of trains and moving through this environment in a much more interesting way. And you start to see that there are people coming in and out, and that you do see the conflicts that start to occur a little bit down here at the turnstiles, the queuing that exists here at the turnstiles and here for the escalators. In a transit situation, you're probably going to accept a little bit of congestion. The question is it acceptable? Are you hitting the levels of service that the transit agency is interested in hitting? Are you getting the journey times and the transfer times between services that are important? And then finally, I'd like to talk a little bit about how it works with BIM and what happens when you have an IFC file that you're going to use to bring in. So if we have an IFC file such as this one, which is created in Revit, what this is a very small sort of sketch of an airport. And you'll see when it comes in that there are baggage carousels, there are check-in desks, there are gates and furniture in the scene. And what Mass Motion is doing is going through this and reading not just the geometry, but also all the object properties that are associated with the IFC objects. So there it is in its raw state. And in the case where you're bringing geometry in from some other application, whether it's Revit or SketchUp or via an FBX file from somewhere else, what you can do is go around and say, these are walls, so I need those to be barriers. The cool thing about IFCs is because there is metadata associated with all those objects, you can also go in, right-click on it, and say, I want to auto-generate all my objects in here. And so it goes through and knows that there are floors and doorways, and it solves all of that for you. So right away, you've gotten probably 90% of the way there in terms of the geometry that's necessary for the simulation. It's not unusual for there to be weird things like this that show up in models where you've got an extra wall for some reason. Not entirely clear why that's there, but it's fine. You can delete it. And then, again, just as we did before, it's just a question of putting in the objects necessary to create realistic simulations. So in this case, we will have people arriving at the curb, say, and making their way up to the gate and waiting room areas up here. A couple of those. And then just setting up, as we did before, the journey that takes people from the curb all the way up to the gate areas. Didn't it like stare actor? And so in those instances where you've brought geometry in that doesn't quite conform to the rules, it'll tell you. So you can go ahead and just fix that until that line goes green. And now that should work just fine. So just that quickly, from your Revit BIM model, you've now got geometry imported and agents moving through your scene. Probably we need to make some provision for some escalators beside the stair because that's not working very well. And if we look at a sort of more completed version of this airport, we'll see that it's possible to not just have people moving through it, very simply from the curb to the gates, but also to have much more complex interactions going on, such that you have people that are able to do check-in and security as well. So now we've got people that, there's a logic which is defining how people are going to move from the curb, go to a particular airline, do their check-in. You'll be able to judge whether or not you have enough positions for ticketing and check-in. Up here, whether or not there's enough provision for security, how the ebb and flow of the crowd is over time. And then a whole range of metrics that could be applied as well. So things like, if you want to know just where everybody is over the course of the simulation. We can now take a look at the pathways that are going to be created by agents moving through this space over time. And there's a range of things that you can do here, including density and journey time and all the rest. So I think that brings me to the end of my time. If anybody has any questions, I don't know if there's time now, but we do have a space over in the exhibition hall. We're under the Oasis banner, and thank you for your time.